Have you guys ever wondered or wanted to explore how to build your own AI models? Well, I wanted to prepare, guys, for you a video and explain how we can build our own AI models to actually solve our own AI problems. So today's model, it's image classification. So what we're going to do today is explore the architecture and essentially how we can build our own AI models. So what we're going to use today, we're going to use a Google Colab. So essentially it's a friendly workspace where you can build and test your own AI models. Google Colab also allows you to access to the GPUs because obviously in order to run these AI models, we need to leverage GPU to run them faster and solve our computational needs in much quicker. So basically, we wanted to explore essentially image classification, and what we're going to use is something called CNN. So it's a convolutional neural network. Essentially, it's a type of AI model that is perfect for solving problems such as image or categorization, image detection, something people normally would use in something like face recognition, even cars driving, self-driving cars would use convolutional neural networks in order to detect objects in the road. So we're going to explore some of this. So this is essentially where you guys can see it's a workspace in Google Colab. So let's first of all, let's name our file, which we're going to call it, let's say it's image classification, and we're going to say neural, we're going to call it convolutional neural networks. And there we go. So this is essentially allows you to type in and use Python type code to build your own models. So you guys please watch along and hopefully you guys learn something. Just essentially it's a first maybe step, and we're going to talk about a bit about architecture, talk about a bit how we can build these models. So and we can explore as well some of the code, so how we can build. So what we're going to do is we're going to use hash, so image classification using convolutional neural networks. So a couple of things also for you guys to learn. The way to navigate Google Colab, you could press Shift and Enter to run the tab and jump into the next tab. Also, you can press Control and M, which allows us to run some of these code. So the way we work and the way you're gonna see, for example, you can create a code that allows you to expand the cells and shorten the cells. So this is sort of becomes like a title or sort of subheading of specific cells. So first of all, we need to set up the TensorFlow. So we're gonna start by just name it, say let's set up our TensorFlow and print the current version. So how are we going to achieve that? We're going to run import function, and we're going to say, as you can see now, obviously this new Google Colab also allows us to autocomplete, but we're going to do it manually for now. So we're going to go TensorFlow as TF. So we can from now on, we can whenever we want to use TensorFlow, we can just write TF, and then we're going to do print open brackets TF dot and then underscore version and then underscore close brackets. So now if we press Control Shift and Enter, as you can see, the spinning wheel shows that currently the code is running. So it's connecting and it's going to show us the current TensorFlow version. So you can see we have a version 2.17 and we are connected now. We established a connection. So we have essentially in the background, we have a virtual machine that's running and powering this Google Colab workspace. I think the key point as well, before I move on, what we need to explore and learn is you have a different tools here in the runtime. So what we need to do is, you can also click it in here. So you can change runtime. So as you can currently see, we're currently using CPU runtime. I think even on the free version, you will have access to a limited number of GPU type of runtimes. I think currently T4 is the fastest. So what we're going to do is we're going to switch and reconnect to the T4 runtime. Mind you guys as well, the important point is we need to do it in the beginning. So I'm going to need to rerun the cell because obviously whenever we switch to the different GPU runtime, obviously it loses all of the code that's been ran before. So we're just going to run the code again to make sure that we have imported TensorFlow. So now let's explore and talk a bit about, so what is image classification? Let's see, for example, let's expand into this. So why would we need to use deep learning for image classification? I'll make it bigger, just make sure you guys can see everything as well. So I think the key point in here to understand, imagine you are building a system that can automatically sort through thousands of holiday photos and group them into categories like beach, mountain, maybe city, and the last one, let's say forest. Let me just close the brackets. So essentially that is image classification in action. So you can essentially create models that will be able to tell based on images, because the way we're going to work, we're going to train a model that's going to create essentially a vector of the feature sets that can detect from a number of images that to know how does the beach look like, how does the mountain look like, how does the city look like, and how does the forest look like. So when we present a new image, it can apply this label and classify this specific image, knowing from previous trained images to say whether that's a beach, a mountain, a city, or a forest. So essentially that's what image classification is. So what we're going to do in this is we're going to use a data set. So let's explore data set. So to build this image, no typos again, to build this image classification model, we need data sets. So one of the most popular data sets for beginners is the Classifier 10 dataset. It consists of 60,000 32 times 32 color images in 10 classes with essentially 6,000 images per class. So that's what we're going to do. So let's think about how we're going to start. So the goal is we're going to start is with model architecture, and then we're going to build essentially a model zero, sort of a starting model. We're going to run our experiment, and then we're going to think and look about potential ways of how we can improve this model. I will also, guys, I don't expect you to obviously become all of a sudden experts. It takes time to practice, to understand how each layer interacts, and then there are options and ways how we can potentially improve and look at every single layer, and whether it's improving, you know, the functions, improving the learning rates, looking at how long the training is going to last. There is a various ways we can explore how we can improve this model. But let's look at first at model architecture. So for image classification, a convolutional neural network, otherwise known as CNN, is a great choice. Now, CNNs essentially are designed to automatically and adaptively, I think that's the very important point, adaptively learn features from spatial hierarchies of features from input images. So let's look at simple CNN architecture. So what we're going to do is we're going to just do some bullet points. So we're going to do this, and then we're going to say input layer, which is going to be the raw values of the image, and then the next one is going to be convolutional layers, apply a series of filters to detect features like edges, textures, and patterns. I think the key point here, guys, to understand is the way AI, or the way we use AI models, it's essentially every layer has a number of hidden neurons. And what these neurons are great at doing, they can each go through layers where they can, for example, if you look at, say, a human's face, there will be a number of layers that will detect how does your nose look like, how does your eye retina look like, how does your ear look like. So it goes through layers of layers that build specific features. Maybe it looks at corner of the images to detect features. Maybe it looks at the features of how does your hair go and change between the edge of your face. So it builds those essentially layers of features and essentially creates sort of a pattern that allows you to later on use these features to detect an image. Then we have another layer which is called a pooling layer. Layers which essentially reduce the spatial dimensions of the feature maps, retaining the most important information. So at this layer, what is happening is that, so as I mentioned, you have, for example, features that detected, in previous layer, convolutional layers, you have detected a nose. Now in this layer, how we can remove as much of noise around those nose features and reduce the size of the image, so we just retain the most important information, and just retain a way, sort of a feature list to be able to detect the nose. And then the next one is essentially a fully connected layers. So they essentially combine the features to make the final classification decision. So, oh, I missed something here. We missed 2 stars just to make it look nicer. There we go. So now have a look at sample architecture. So our sample architecture. So here is a sample CNN architecture. So what we're going to do is, for this sample architecture, the way we're going to build it is we're going to use convolutional layer number 1 is going to be 32 filters, and then we're going to use 3 times 3 kernel size, and we're going to use ReLU activation function. Then what we're going to use is we're going to use also a max pooling layer, and number 1, which essentially is going to be 2 times 2 pooling window. This guy knows us too well as well, so we're already predicting what we're going to say next. So let's have a look. No, we just want pooling window. Don't do too much help. And then the next one is going to be convolutional layer number 2, which will be 64 filters, and then again we're going to use 3 times 3 kernel size and ReLU activation function. And then the next one is going to be again another max pooling layer. And this time we're going to do the same. So we're going to do 2 times 2 pooling window. And then we're going to do the fully connected layer. And what we're going to do there is essentially we're going to do 128 neurons and ReLU activation. And then the last but not least, obviously, we're going to do output layer, which is going to be 10 neurons. So the important point is 10 neurons. We're using 10 neurons here is because 10 neurons for each class of the images. So 10 neurons for the 10 classes, and we're going to use softmax activation. So there you go. There is our sample architecture. Obviously we don't need that. We're gonna just tidy it up, and there we go. So now actually let's go and build the actual model and see how it looks like. So let's build the actual model now. So what we're going to do is we're going to start from TensorFlow.keras, import data sets, layers, and models, and then import matplot library.pyplot. So this is essentially a great library to use to essentially do plot our loss functions and loss curves. So you will see, guys, as a show, because it's a great way to essentially allow us to see how a loss function is doing basically as we're training our model. So what we're going to do now is we're gonna load and pre-process the Classifier 10 dataset. So the way we're going to do that is we're going to call our datasets. So it's going to be train images, train labels, close the bracket, comma, and then we're going to use test underscore images, comma, test labels, and that's going to be equal data sets dot Classifier 10 dot load data. So there we go. So key point here to understand, guys, as well. So we need 4 types of labels. So we're gonna have a training labels, and we're gonna have testing labels and images. So why we split it up is because obviously the way we're gonna do this is we cannot test our model on the same images. So that's why normally what we do is we split our data into, normally sort of, we have it between how you want to do it is people split between 75 and 25% or 80-20, but normally you have, say, 75% of data set will be your training images and 25% will be your testing images, basically where we're going to use the test validation to check how our model is behaving. So we load the data, and then the next line what we're going to do is we're going to use train images test images equals train images divided by 245.0, and then test images divided 245.0. Now the key point while we're doing this here, guys, is you need to understand that every image has a color channel of 255 pixels. So while we're doing it, essentially we're trying to split or translate our images into numbers. So that's why normally we do this division to essentially translate images into essentially a number. So what's the what's the current pixel of a specific encoding. So on to the next line, we're going to actually define our CNN model. So let's define the CNN model. So what we're going to do in this part is we're going to write, so our model is going to be equal models dot sequential. So we're going to use sequential model, and then we're going to open the brackets, and then we're going to start in the next line. So we're going to start doing our layers. So first layer, as we mentioned, guys, in an architecture, we're going to do a convolutional layer. So we're just going to do layers dot conv. We're going to do 2D convolutional layers because we're doing images. There are 3D convolutional layers and all kinds of other layers, but because we're only using images, we only need a 2D. So we're going to use 2D, and then we're going to open the brackets again, and as I said before, we're going to use 32 filters, comma, and then we're going to do the kernel size, which is 3,3. I'm going to close the brackets, and then comma, we're going to use the activation here. So it's activation equals, I'm going to do in relu, and then we're also going to use here our input shape, which equals and the input shape is, as I mentioned before, the images are 32, 32, 3, and then essentially double close the brackets, and that's our first convolutional layer in our model. Now next layer, as I said in the sample architecture, now we're going to have to build a max pooling layer. So again, we're going to type in layers dot max, and as you can see, it's already helping us to complete. So max pooling, again, same 2D, and this time it's just going to be 2, 2. As I said before, as you can see, guys, 2 times 2 pooling window. So that's what we're going to do in here. Again, comma. Again, we're doing another convolutional layer. So this time again, we're going to type in layers dot conv 2D, open brackets, and this time we're going to use, as I said just above, we're going to use 64 filters, and then we're going to do again 3, 3, so kernel 3 times 3, and then we need to again call out an activation. So it's going to be activation equals relu, and comma, just making sure we have correct commas. Yep. And then the next line we're going to be again layers dot max pooling 2D, and then again we're going to be 2, 2, close it. So max pooling layers, that's all complete. Now the key point, what we're going to do is, another important point is, we're going to flatten all of the layers, because what we want to do is, at this point, what we want to do is with flattening is essentially convolutional and max pooling layers. They create a lot of these features, and we want to flatten that feature to make it easier and make it less, essentially. So we're going to extract the most important information, as I said, for you guys. So essentially it's like I mentioned to you guys before, is so essentially flatten is it's doing the fully connected layer. So essentially it's essentially combine the features and extract the most important information. So it's just what it happens out of the pooling layers. So the way we're gonna do the next one is we're gonna do we need to add a few more layers. So the next layer will be layers dot. So the last few layers is going to be the dense layers. So going to be first, as I mentioned, is going to be 128 neurons layer with, again, activation equals, we're going to do relu again. Relu, and then we close this, and then the last layer, last dense layer is the essentially number of 10 neurons for each class, and we're going to use this time a softmax activation. So what we're going to do is 10 activation, this time is going to be softmax, and that's pretty much it. So that's essentially the definition of our model. Now what we're going to need to do next is we need to compile the model itself. So what we're going to do is we're gonna compile the model. So how we compile is we're gonna essentially type in model.compile, and then we're gonna use the optimizer. So the optimizer in this time, and most of the times that you guys are gonna build your own models, it's gonna be Adam. And then what we're gonna use is we're gonna use loss function. So how we're going to measure loss in this time is going to be sparse categorical cross entropy. I'm not guys going to go into mathematical details. Guys, if you really want to explore and learn more about this, please explore. You know, there's different optimizer functions that you can use. Adam is the best optimization for the model sort of loss function, because it's usually it's adapted to the best for its ability. So that's why we use. You can learn, especially I think the great courses that you can look at it. So MIT provides their own lectures from building their own AI models, and you can learn so much from them. So please have a look at MIT courses on YouTube, and just have a look at some books. As you say, you can Google loss sparse categorical cross entropy, or how to use optimizers such as Adam, and you can learn so much more. But I just wanted guys to show and walk through first model and how we're going to build, and then we're going to run it and just see what's the output is. So also we need to measure our metrics. So metrics is going to be we're going to measure accuracy, and that's pretty much it. So now we're going to need to train the model. So we're going to create a variable called history, which allows us to then later on to map and create a graphical representation of our loss functions. So what we're going to do is we're going to do here model.fit. So essentially we're fitting the model, and what we're going to fit is we're going to fit train images and train labels. We're gonna type in epochs. So epochs is essentially, it's a very important part here as well. So as you train your models, you can tinker and play around how many epochs we use. But epochs is essentially is a one training cycle that we complete. So depending on how many layers and how many neurons you have, these epochs become longer and longer to complete. So again, you sometimes will need to think about speed versus accuracy. So depending on what use case you're using this model. So if you're running, for example, this classification somewhere where it's exposed to your customers and you want to get a quick answer, sometimes you'll probably sacrifice accuracy for speed and vice versa. So you just have to think. So we're going to run 10 epochs for this. And then we're going to do validation. Data will be equal to test images and test labels. And then we're going to evaluate our model. So evaluate the model. And let me just, I can see we had one too many dots. So evaluating the model, we're going to do test underscore loss and test underscore accuracy. It's going to be model dot evaluate, and then we're going to do test images, test labels. You can set verbosity in however much you want. We're gonna, for this purpose, we're gonna set verbose equals 2. And then the last but not least, what we want to do is we're gonna plot training and validation accuracy, and gonna plot training and validation loss values. So let me just, and that's why we imported this matplotlib, because it allows us to essentially much easier to plot it. So let's plot training. Yes, we know we will be utilizing our GPU in a minute, just leave us alone. Training and validation accuracy values. So how we're going to do is we're going to do plt.plot, and then what we're going to do is we're going to put in brackets, it's history, and then in this we're going to type in, we're going to need accuracy, and then next one is going to be plt.plot, and then this again is going to be history, but this time we're going to plot val accuracy, and then next one is going to be plt dot title. So we can call this plot however much we want. So for this one we're going to call it, let's call model accuracy, and then we're going to name the axis. So plt dot y label is going to be accuracy, and then plt dot x label, it's going to be epoch, so how many epochs we run, and then how the accuracy looks like after each epoch. Let me just remove that and put a dot, and then we're going to put plt dot legend, and in here we're going to showcase essentially, sorry, there's this, and then we're going to do train, and we're going to do validation, comma, and then we're going to do lock equals, we're going to do upper left, there we go, and then plt dot show to make sure it shows that, and then the last one we're going to just do plot training and validation loss values. So again, plt dot plot, just going to do it quickly for you guys, history dot history, and this time I'm just going to use loss, and then plt.plot, and then we're going to do again history dot history, and this time we're going to use val loss, and then we're going to do plt dot title. So this one's going to be called model loss, and then again we're going to do plt dot y label. So we're going to name the label y axis, and it's going to be called loss, and then plt dot next label. It's again going to be the same. It's going to be epoch, and then we're going to do again the legend. So plt dot legend, and then we're going to set up again. So it's going to be train, validation, and then we're going to be doing lock equals upper right this time, and the last but not least plt dot show. So hopefully we didn't make any errors. So we press Control Enter and let it run. Ah, we missed something. What did we miss? Sparse, categorical, cross entropy. So perhaps we missed a comma. Yes, we definitely have missed a comma. So we missed a comma here, so let's try again. Ah, we missed again something. Expression cannot contain assignment. Perhaps you meant double equal. So what will we need? PLT legend. We need it here, we need it comma. Yep, that should be correct. There we go. So we're loading the data first of all. Again, we're missing something. Define the model. Layers con to D. Perhaps we missed a comma. Perhaps we did. Let's have a look. Where have we missed a comma? So let's have a look. We got this. Actually, let me do this a little bit different experiment, because obviously we don't want to run the data every time. So what we're going to do is, what I'm going to do, guys, just while we are here, and it's good, I guess, learning, practice, and experiment. So since we got the data loaded, let's put this in here, and let's delete this. So we can split it out. We don't need to load the data every time we run the cell. So let's do this. So let's run this. So we can just load the data. So data has been loaded, and now let's run this. So float object is not callable. So we had something to do with our data to do with float. Ah, there we go. I found a mistake. There we go. Let's try again. Too many errors, guys. Input shape, not sharp ray, input shape. There we go. Let's see if this int object is not callable. So what do we have here? We missed again. Guys. There we go. Third time lucky is a charm. So we got our model now, and it's going to complete and run through 10 epochs. So as you can see, is running 1563 experimentations. So we're getting, as you guys see, 4 types of measurements. So we're getting accuracy, loss, validation accuracy, and validation loss. So the main point for us is, and the main number we're looking at, we're not looking at accuracy, because accuracy on the training set is very easy to achieve very high accuracy on the first number. What we are the most concerned about is validation accuracy. So when we're validating against a new set of data, what's the accuracy there? I think that's the most important. We don't want to get, high accuracy on the training set is not necessarily a bad thing, but it's not something how we evaluate and measure our model's effectiveness. Our sole goal and purpose is to achieve as high possible validation accuracy. So there we go. We're coming up to the last epoch. We made an error also with the plot. So what I'm going to do is as well, guys. Yeah, I can see. Just for you as well. So let's pull it out of here. Again, split it out. Sometimes it's not good to have, I guess, too many things in one area. So we can see, obviously. Let's delete and remove this. And I'm going to do these separate. So first of all, let's have a look at first things first. So as you can see, guys, after 10 epochs, we have the numbers here. So we have accuracy of 70.76%. And we have a loss down to 0.96. So loss is just obviously the measure of how much it's losing essentially, but that's not the most important part. So let's actually collect the errors and see how these graphs will look like. So history. Let's try and plot them now, just to get a graphical representation. We got another error. What's wrong in this? So we got PLT, this needs to be. So let's rerun them again. Again. There we go. Let's get this time right. So there we go, and this is our essentially accuracy between training accuracy and validation accuracy expressed in a graph, as well as loss. So the key point here and what you guys need to learn, and as and when we explore, let me just zoom in, I guess, guys, for you to see better. The most important way we need to explore this is that these graphs should pretty much mimic each other. So currently, as you can see, the data is underfitting. So you can have data that can be overfitting or underfitting in our model, but they should essentially follow a similar type of graph. They should move together sort of side by side, and similar to the loss. So therefore, our next goal in our experimentation would be to look at these models and think how we can change the parameters to improve the training. So what would I would do, for example, as I say, so this is our model that we just built. So now we can think about how we can change number of things. So as I said to you guys before, we can change epochs, we can change the type of activations that we potentially have, we can change the number of layers. So for example, layers is again point is another point, is where we're looking at layers. We need to look at multiples of 8. The best way to do layers is multiples of 8. So again, we can explore here again, change this 32 maybe into 64, maybe this 64 into 128, maybe this 128 in 256, in maybe 512, maybe 1024. So the key point in sort of AI model development, it's scientific, essentially experimentation. We just have to test and test and test until we are happy to the level of accuracy, because currently the way our model will predict, out of 10 images it will apply 7 labels correctly, so we got 70% accuracy. But our goal is, in the best models, the way they perform, they're reaching accuracies of nearly to 90%. So I think none of the models are going to reach ever 100% accuracy, but we can arrive at around 80, 85, even up to 90% of the best models. So for you is, I guess, a task or way into the learning curve is to understand how these models work and how we can change some of these layers, some of these experimentations, and to try to achieve as high of a percentage as possible. So guys, hopefully you learned something in your AI journey. Please reach out if you want to learn more. Also let me know if you want to see a follow-up videos where we can actually talk about how we can explore these different layers and essentially eventually get a high enough accuracy score. But it's a first snippet in your AI journey, building a convolutional neural network in image detection. I think AI is probably the area where it's going to impact the world the most. So you being able to learn and explore that journey and and practice and get better at it, you will reap so much benefit. So hopefully you guys enjoy it. Please like, subscribe, follow the channel. The more people engage and follow the channel again, that gives us more benefit, and more hopefully allows us to deliver even more value to you guys.